So, even outside of the option setting, just when it comes to investing, say in the stock market, it's useful to kind of be able to compute a few statistics for the underlying model of the price that you have. So, if here in the first line we're computing the expected price of that stock or that asset in general at time t. And if an expectation that price goes up, then you may want to invest and purchase that stock, so that later, when perhaps indeed the price does actually go up, you could sell it to for a profit. Right? So that's a sort of what we call, I guess, speculative trading. And kind of a secondary consideration, but no less important, is sort of what is your uncertainty associated with that prediction. So you compute the expected, what you expect the price to behave like, and maybe you have even a plot of the expectation of x versus time. And the second consideration, like I just mentioned, is computing the uncertainty, which is typically associated with the variance or standard deviation, which is the square root of that variance. And so once you have that, you can kind of get a sense about sort of the price is going to be, I expect the price to be such and such. It's that mu t variable denoted by mu t. And then, I'm going to guess that it's within, a couple of standard deviations, or maybe within a standard deviation. And that's the square root of the variance. And so, even outside of sort of options, these are useful things to be able to compute. And here, I just want to point out a few kind of some of the technical challenges that you could come up with. So, the first thing is you can always write for an expectation, just, the expected value is just whatever the value of the random variable is. And here I've denoted it by z. And I'm integrating against the cumulative distribution function, so this is just notation for what that expectation actually is. So that part is always true, but here you want to be careful. If your CDF is differentiable everywhere, meaning the density, the probability density function exists everywhere, then you would just switch that big f of x dz to be the probability density function at z times dz, and carry out that integral. We've already seen, however, that the CDF has this discontinuity, so you have to be careful and sort of isolate this point, namely the point 0, the origin. And the reason for isolating it is because like we've discussed, no density exists here. And so what I've done here in this calculation is just split out the integral into three terms. The first one is this range here from minus infinity up to 0, not including 0. And we know there's different ways to actually indicate whether you include 0 or not, but here I'm just kind of telling you that I'm not including 0 for the obvious reason that there's a jump here. So fortunately we know that there is a density on this half open, or I guess open interval from negative infinity to 0. And the density there is 0, and so regardless of the z here, the density on this between these limits is 0, and so this whole integral just goes away. The next one is, I guess let's treat the actual point of discontinuity. So this would be treated very much like a discrete random variable. You have what would be called a probability mass concentrating at one point, namely p0 is clearly strictly positive, so there's a lot of probability mass concentrated at a single point, which makes this distribution not really continuous. But here's what here's how you treat that. Right? We've isolated that case. We're looking for an expected value of the price. What's the price? It's 0. What's the probability? It's p0. You multiply those two, and fortunately this just goes away. And if it didn't, we know how to compute this guy, and we can handle that as well. And then the final region is here. This is the half open interval from 0, not including 0, up to infinity. looking for the expectation of z and plugging in this density here. So, in the end, we see that this is what the answer reduces to, and, at this point, you kind of, sometimes you can leave it, the way it is. Sometimes you can try to, simplify things. I'll show you kind of there's a lot of references online that you can see about how to evaluate, all these integrals. So, a lot of kind of even books just catalog all these integrals against the standard normal density. So here, phi and big phi are the probability density and the cumulative distribution function of the standard normal. And then, kind of you see the link up on top, so you can find this page, and then, there's all manner of integrals that sometimes have explicit expressions. It's mostly rare, though. You see how the limits there for these definite integrals usually go from 0 to infinity or minus infinity to infinity, and the reason is that they're really trying to exploit the symmetry of this distribution, kind of partitioning it, at the midway point, which for the standard normal is, at the origin. And so sometimes you just can't, you can't simplify any further. What people usually do in this case is try to write the answer at least in terms of some, basic computational unit, which is, typically taken to be the CDF of the standard normal, and that's often written in terms of this error function. You see it there, and you can read about it just going to the link there. These things are kind of implemented well in a number of kind of statistical and computational packages, so you kind of trust that computation, as long as you can express your answer in terms of that error function or the function big phi, you're kind of have done a good job. Here I have something a little bit different, but function big psi, this is the density of not the standard normal, but the normal that's at mean x and standard deviation sigma squared of t. But at the same time, you can always change variables, as we've done, just I think in the previous clip I covered that. So this is the standard normal density, and it's equal to this integral as long as provided you change the limit of the integration. So make sure you're comfortable with that. So sometimes you can, in this case, it's unlikely that you can simplify this, any further, unless you have a special setting for x. Like when x is equal to 0, you'll probably be able to get a nice clean answer here. But otherwise, that's unlikely to be the case. Let me just point you to a few tricks that you could try to work to express the final result, maybe in terms of this big phi, or maybe this I guess I don't know which one is phi. This one is phi and this one is psi, so either one, but I guess big phi is more standard. So one thing you can look at is the derivative of the normal density, meaning the derivative of this with respect to z, and you'll see immediately that it just basically gives back the density itself, multiplied by whatever was there left over from the chain rule. So I took an extra derivative of this and placed it out here. The two canceled. I picked up a minus sign, so I flipped the x and the z. And why do this? Well, you get right away a nice relationship between phi x multiplying a z, which is what we're integrating, say over there, and a derivative, and then you can try to reconstruct from, by the fundamental theorem of calculus, you can try to reconstruct what that final integral could look like in terms of, maybe big psi, or again, the function big phi, which is here. And then you have something kind of in standard form. There's another trick that sometimes is useful, which is integration by parts, and so this is a way of transferring kind of one derivative of the integrand from the other. So if in the integrand you have kind of two functions, you can try to rewrite it as a slightly different integration problem. You see how we went from the derivative on the v transferred over to a derivative on the u, and so that's often pretty useful. Here the limits a and b were, perhaps they look like they're finite numbers, but they can be carried out to infinity, in which case that first part, the leading couple terms, those often go away, especially if you're dealing with densities. They vanish infinity, so that kind of helps you to transition to a slightly different integral, and then maybe you look up something in a table and it's something that's familiar. Okay, and so the final kind of note here is expected payoffs, right? You can now the same way we've done we computed the expected price and the uncertainty in that price. It's then not too difficult to carry that over, that intuition and the math over to an expected payoff. Certainly, if you're going to make a decision as to whether to invest in this contract, it would certainly be a good thing to try to compute out how much on expectation you stand to make from investing or purchasing this option, and then maybe even compute its variance, which kind of gives you the uncertainty associated with that investment.